Okay, so we're going to look at the relationship between exponentials and logs, and we were talking about exponentials the last time, but this time we're going to look at how, for example, this exponential function can, its inverse will really be a log function. We've said a lot about the relationship between exponentials and logs being inverse functions. So if this was 10 to a power, and the input is a power, an example would be if I was finding f of 2, 10 to the second power is 100. But over here, if I went and found its inverse, if the input here is an exponent, then it must be that in the case of the inverse of this exponential, a log function, the output must be an exponent. So for example, if the output to this exponential was 100, and I said I'm going to find the log base 10 of 100, I'd be saying 10 to what power will give me an output, will give me this 100, and the output to that log function would be 2. 100 would be the input, and the output would be 2, the very exponent that was the input to the exponential that gave you 100. And once again, for example, since 10 to the third is equal to 1,000, if I was looking at it from a log standpoint, I could say that the log base 10 of 1,000, the exponent on a base of 10 that gives you 1,000 is 3. So here the input is the exponent, the output is 10,000, or 1,000. Here the input is the 1,000, and the output is the exponent on that base of 10 that would give you 1,000. Okay, so we're going to use that for the basis of working through a bunch of 6.4 problems. And the first problem, number 13, right out of our book, is this, that if we went and looked at this initial exponential equation, there, and let me see if I can get this to, I'm going to adjust this light here a little bit to keep it from washing out so much, see if that'll help. So if I have this and I want to turn it into a log, remember the output to a log, the answer to a log problem is always the exponent. So what I like to do is I say, all right, well, I know if I'm converting this to a log, I know that at least the answer to it is the exponent, 2. Because of inverse relationships between exponentials and logs. If the input is 2, the output to the log must be 2. And the base will be the same. So if this is a base of a in the exponential, it's a base of a. And if the output to the exponential is 1.6, the input to the log is 1.6. So we're saying a to the second power would give me 1.6. In other words, the log base a of 1.6 is 2. 2 is the exponent on a base of a that gives me 1.6. Okay, let's try that again. So here's another one. 3 to the x is equal to 4.6. This is problem 16 out of the book. And if I looked at this, I would say, excuse me, that I know that the output to my log is an exponent, and therefore I should get x. I know my base is 3, so I'm taking the log base 3 of 4.6, and that is x. So 3 to the x power should give me 4.6. By the way, this is the beginning of taking a look. If we went and took our calculator and calculated this, we could get an answer for this exponent. Logs have the ability to go ahead and get answers to exponential situations where the exponent is unknown, because that becomes the answer in a log problem. And we'll talk more about that on another video. Okay, so let's go ahead and take a look down here, number 19. Now this time we're going the opposite direction. We're going to start with a log, and we'll go to an exponential, right? So in this case, we have the log base 2 of 8 equals 3. And converting that into an exponential would be 2 to the third power gives me 8, because the answer to the log is always a power. So 2 to to the third power is 8, which we know 2 times 2 times 2 would give you 8. And look at, so the log base 2 of 8 says what exponent on a base of 2 would give you 8? It is 3. Okay, let's look at this one. Number 25 out of the book. The natural log of 4 equals x. Well, natural log always has a base of e. So this is e to this power, always the output to a log, is equal to 4. Okay, let's take a look at finding exact values just to see that we understand the concepts of logs. So what we're saying here is 2 to what power, because remember the output to a log is a power, 2 to what power would give me 1? 2 to what power would give me 1? Well, 2 to the 0 power gives me 1. Anything to the 0 power is 1. So the answer to this is 0. How about this one here? 10 to what power gives me 100? Well, we know that 10 to the second power gives me 100. So this would be 2. And how about this? Well, this is a little weird, So we do have a base of e. We know that because it's a natural log. So we're saying e to what power gives me the square root of e? E to what power, right here, gives me the square root of e? Well, remember, square root in its rational exponent form is e to the 1/2 power. So the power in the box that would give me that result would just be 1/2. So this answer is 1/2. Okay. All right, one more. Excuse me again. Okay, right here we have, we're asking 3 to what power would give me 1/9. Well, I'm going to really have this kind of situation. 3 to some power is giving me 1/9, which I could rewrite here a little bit, because I could say that 1/9 is really 1 over 3 squared, which is equal to 3 to the negative second. So we know the answer right here is -2. 3 to the negative second power would give me 1/9. And the answer, I guess I could put it in both boxes, would be -2. Okay, let me flip this paper over and we'll take a look at what else is in 6.4. There are going to be some log equations, and we're going to be able to use our relationship between logs and exponentials to go ahead and solve these. For example, on this problem right here, that I don't know x, but I can say this. I know that on a base of 3, I'm really saying that 3, and remember the output to a log is always a power, so 3 to the second power is equal to x. I converted to an exponential, and x would be 9. But on a practical level, it makes sense that the log base 3 of 9 is 2, because 3 to the second power would give me 9 right here, right? Let's try another one. Okay, now by the way, when I go to do this problem, I think what I'm going to go ahead and do is I'll isolate the exponential piece of this. So I'm going to divide by 5 here. So I have this. E to the 0.2x is equal to 7/5. Now I'm going to go to logs, and I'll say the natural log, since I have a base of e, the natural log of, and by the way, what I'm taking the log of is the output to the exponential, right? The natural log of 7/5 is equal to the exponent of 0.2x. And now, if I was going to go ahead and solve this, I could divide both sides by 0.2. And I have x is equal to, and by the way, if I put a 1 here, 1 divided by 0.2 is 5. So I could say this is 5 times the natural log of 7/5. 5 times the natural log of 7/5. Okay, let's try another one. So this one, I'm going to go ahead and let's see here. Well, we know that the answer to a log is always a power. So this is 3 to the second power is equal to 3x minus 2. 9 is equal to 3x minus 2. I'm going to add 2 to the other side and divide by 3. So x is equal to 11/3. Okay, one more problem. Once again, I think I'll isolate just the exponential part of this and divide by 2. So I got 10 to the 2 minus x is equal to 5/2. And then, excuse me, I'm going to go ahead and turn this into an into a log. And I have a base of 10. I know my answer to my log is the exponent. And so I'm going to say that the log of 5/2, base 10 of 5/2, is equal to 2 minus x. Then I'm going to go ahead and I'll subtract 2, and I'll get this. Minus 2 is equal to, now be careful, this is negative x. So I'm going to just multiply by negative 1 on both sides, and this become positive, this become negative, and this become positive, and there would be our answer. And we could certainly turn this answer around as well and call it 2 minus the log base 10. And by the way, we've probably talked about this before, but I don't have to write base 10. It is assumed when you don't have any base on a log that it is base 10. I'll go ahead and I am going to do these problems, but I think I'll save them for a second 6.4 video, which that way I won't make this video too long. We're a little over 12 minutes the way it is.